Welcome to the Explainer. Today, we're diving into a massive leap forward in the world of browser-based machine learning. We're unpacking Google's latest documentation from their AI Edge ecosystem, and specifically, we're zeroing in on a total game changer for WebAI, LiteRT for web, with LiteRT.js. Now, if you've been working at the intersection of web development and AI, you already know the browser is kind of the ultimate frontier. But let's be real, it's also been one of the absolute most frustrating environments to actually tame. So it all comes down to the million-dollar question, doesn't it? How on earth do you run complex AI in a browser without literally melting your user's CPU? Historically, running machine learning models natively on the web has meant dealing with a ton of friction. I mean, we're talking massive performance bottlenecks, sluggish execution, and a workflow that honestly feels like trying to fit a square peg into a round hole. Because obviously, you want to deliver these incredible cutting-edge AI experiences directly to your users with no server round trips, but you absolutely cannot afford to drain their battery in 5 minutes flat. Okay, let's dive into this. Today, we're taking the exact developer journey to solve this massive web AI problem. First, we'll meet LiteRT.js, explore its 3 core features, and see how it simplifies model conversion. Then we'll integrate it into TensorFlow.js, and finally, update our inputs. Let's get started. All right, kicking things off with Section 1, meet LiteRT.js, Google's production web AI runtime. So, LiteRT.js is Google's brand new, high-performance web AI runtime. And what makes this so incredibly important is that it is explicitly targeting production web applications. This isn't just some experimental sandbox, right? It's a continuation of the broader LiteRT stack. That means it guarantees multi-framework support and effectively unifies Google's core AI runtime across all platforms. Basically, you're getting the exact same robust foundation on the web that you'd expect in a native app environment. Moving right along to Section 2, 3 core features, or as I like to call them, the superpowers of LiteRT.js. There are 3 core capabilities here that should make absolutely any web developer sit up and pay attention. First up, hardware-accelerated inference directly in the browser. Second is multi-framework compatibility. Now, this one is huge because it means you get native support for compiling from PyTorch, JAX, and TensorFlow. You're not locked into just one ecosystem anymore. And third, you get the ability to iterate on your existing pipelines right out of the box. Now, what's really interesting about this is how it actually achieves this incredible hardware acceleration. We have to look at the APIs. For the CPU side of things, it uses XNN pack mapped to lightweight WebAssembly, which already gives you exceptional performance. But when it comes to scaling up to GPUs and dedicated hardware like NPUs, well, LiteRT.js natively surfaces both the WebGPU API and the emerging WebNN API. This essentially empowers you, the developer, with fine-grained platform-specific optimization across different browser architectures. It literally unlocks the full hardware potential of your user's device, all securely within the browser. But, how do we actually get our models into it? That brings us to Section 3, simple model conversion, the direct path. Honestly, this might just be the biggest workflow improvement of the entire package. Seriously, just look at this contrast. If you've ever tried converting a PyTorch model to run on the web before, you know the agonizing multi-step nightmare of the old pipeline. You'd take PyTorch, export it to Onyx, try to push that into TensorFlow, and then finally convert it for TensorFlow.js. It was a super brittle process where things could break at literally any point. But now, it's a sleek, single-step reality. You go directly from PyTorch to LiteRT using the LiteRT torch converter. It is a straight, direct path, just a massive relief. And the really beautiful thing here is that LiteRT.js uses the universal .tflite format. So not only is the conversion process massively simplified, with dedicated debugging tools to help you out along the way, by the way, but you can also just grab existing models right off Kaggle or Hugging Face and use them natively. The amount of time this saves for development teams is just staggering. Now, for those of you with existing apps, we're moving to Section 4, TensorFlow.js integration, the practical guide. First off, I want to reassure you right now, you do not have to rip out and rewrite your entire architecture. As the documentation clearly states, LiteRT.js is designed to function right within your existing TensorFlow.js pipelines. It is fully compatible with your current pre- and post-processing code. You literally only need to migrate the model execution itself. That's it. The migration process breaks down into exactly 5 steps. First, as we just talked about, convert your model to .tflite. Second, you're going to install a couple specific NPM packages. You'll need the @LiteRTS/core and the tfjs-interrupt packages. Third, import the TensorFlow.js WebGPU backend because you'll need that for the interop to actually work. Fourth, replace your old model loading code with the new LiteRT model loading code. And finally, pay close attention to this one. Step 5 is substituting your predict execution. So the crucial point is exactly how you handle that substitution in step 5. You're going to swap out your old model.predict or model.execute calls with a brand new function called run with tfjs tensors. What makes this so elegantly brilliant is that this new execution function accepts the exact same TensorFlow.js input tensors you're already passing in, and it outputs the exact same TensorFlow.js tensors you're already expecting. It creates this completely seamless boundary between your old pipeline and this blazing fast new runtime. Finally, let's wrap up with section 5, updating model inputs. This is just the final refinement, a quick cleanup phase to ensure your data flows perfectly. When you use the converter, it might slightly alter the layout or the naming of your inputs and outputs compared to traditional TensorFlow.js expectations. So just run through this quick checklist. You might need to reorder your inputs depending on how the converter sorted them. You might need to transpose your inputs or outputs to match the new layout. And if your code relies on named inputs, just be aware that you might need to rename them to match the new .tflite structure. And this brilliantly illustrates how the API supports you through that process. You don't have to blindly guess what those new inputs and outputs look like. You can simply call model.getInputDetails and model.getOutputDetails to inspect the exact changes right there in your code and then map them accordingly. It is incredibly developer-friendly. So, we've seen how LiteRT.js brings true hardware-accelerated multi-framework performance right to the web. We've seen that direct conversion path, and we've seen how seamlessly it integrates into the tensor pipelines you've already built. The friction of WebAI has literally never been lower. So I'm going to leave you with this question to ponder as you open your code editors today. What will you build now that the browser is officially a powerhouse AI engine? Thanks for joining me for this explainer, and happy coding.